Jain everyone. Myself Shruti Jain, Assistant Professor from MCA Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today we will be talking about the software design topic, wherein we will be focusing more on the coupling and the cohesion part. This topic is covered under Software Engineering KCA 302 is a code for this. So coming to software engineering, we till now what we have discussed in the previous slides or in the previous videos, we talked about the SRS and how a software is to be created. Now SRS was the part of the software requirement. Now comes the software design. Once all the requirements are gathered, we proceed to the designing of the software. So when it comes to the software design, it is more creative than we analyze the software, because the software development depends upon the designing of the software. And this is also known as the problem solving activity, wherein the problem is already analyzed in the SRS. Now we'll be designing how the software will actually look like and how it will be provided to the customer. So if we talk about what a design is, so the design basically talks about how a software is to be developed, and this how is implemented in the software design document, that is the SDD. So in the first phase we discussed, while we gathered the requirements from the user, that it is in the form of SRS. Now the next phase is the software design, where we design the document in the form of SDD. So let's understand what a software design is. Software design is a software engineering activity where the software requirements are analyzed in order to produce a description of the internal structure and organization of the system. This actually serves as a basis for the construction. That is, the next step after the software design is a coding part. So this software design actually helps the developers in order to provide it a coding platform that could be in any of the language. So this is a base for the coding. So now if we talk about the designs, we have two types of designs. The first one is a conceptual design and the next one is a technical design. Now if we talk about the conceptual design, it is more related to the customers, where the customer knows like what all things need to be implemented in the system. The technical design is with the software developers who know how to implement those things in the design. So because customer is a layman person, he doesn't know anything much about the technicality of the software. So they just tell how the software looks like or what are the requirements in the requirement phase. So the conceptual design is for the customer so that he understands what all things will be provided to him. But the later part, the technical part, is with the development team, where they design it technically so that it is helpful later in the coding of the software. So characteristics and objectives of a good software design. The first one is the correctness. So we all know that if the software design is correctly implemented, then it will be helpful in the coding of the software. If the design is incorrect or it has some loopholes, that will affect the coding of the software, the later phases of the software basically. Understandability, the design should be clear enough that it is easily understandable. Efficient, it should be efficient so that whatever expectations are there with the software design are all implemented in it. Maintainability, it is easily amendable, maybe later on in the phases where the maintenance needs to be done in a software, then we can easily implement the changes in it and it can be done at a very easy pace. Now we have some of the principles in software design. The first principle that we have is modularity or decomposition. The second principle that we have is coupling cohesion, top down and bottom up strategies, complexity in designing and abstraction. Out of these 5 design principles, we will be majorly focusing on coupling and cohesion. Before that comes a modularity and decomposition, wherein we basically we make a design in the form of, we break the software into different modules. the modules are independent modules which can work independently, and like they can be independently worked upon, and they are interrelated with each other. So since a big software cannot be developed as a whole, that is why we divide it into different modules or into different sections, so that each can work independently in itself, and together when we combine all those modules, they are interrelated as well, and they all become a single software. So based on this modularity and decomposition, we come to the coupling and the cohesion part. Now coupling and cohesion are basically two things that again depends upon the modules that are already being created. So coupling basically talks about the interdependence of two modules on each other. So as we consider it, if there are two modules which are separately created, if the two modules are interrelated to each other very highly, like one is highly dependent on each other, the working of one module affects the working on the other module or the other module. In that case, if a bug occurs in module A, it will directly affect the module B, and debugging would be little difficult. So we always say that high coupling between the two modules should be avoided. The two modules should be interconnected with each other, but they should be loosely interconnected. Loosely interconnected means if they are interdependent on each other, that degree of interdependence should be low. So coupling is a measure of relative interconnection among different modules. So as we discussed just now, coupling is high between the components if they depend heavily on one another. Example, there is lot of communication between them, and coupling is loose if there are few dependencies between the components. If they are loosely interdependent on each other, finding the bugs and debugging would be easy as compared to if the two components are highly coupled together. So this shows the high and the low coupling. So if we talk about these modules, this is module suppose 1, this is module 2, this is 3, and this is 4. All the 4 are uncoupled, there is no dependency between the two modules. But if we look here, these 4 modules are interconnected with each other, but their dependency on each other is very low. Like one is only going in one direction with 2, here they both are interconnected with each other both ways. Again 3 only is one way interconnected, while 4 and 1 are connected both ways. So this is an example of loosely coupled modules. Now if we talk about highly coupled modules, now as you can see, we have a lot of communication lines, interconnectedness between them. So this shows that these modules are highly coupled. These modules have a lot of dependencies. Therefore, if suppose a bug occurs in module 1, it would be affecting all the modules somewhere or the other way. Debugging would be a little bit difficult as compared to the loosely coupled modules. That is why we recommend, it is recommended that the the modules should be coupled very loosely rather than being highly coupled. Coming to the different types of coupling, the first type of coupling that we have is a data coupling. So two modules are data coupled if they communicate through parameters. Communicating through parameters over here means, suppose I have two modules, this is module 1 and this is module 2. The module 1 is there to retrieve the customer's information, and module 2 retrieves the customer's address. Now this customer ID would be used in order to retrieve the customer address. From here, if we pass on the parameter of customer ID, as customer ID is unique for each and every customer, so with the help of this customer ID, the customer address could be retrieved and it would be going to the module 1. So when the two modules interact with the help of parameters, the parameters again are of very basic data types, like These are of simple data types, or in case a record being passed as a parameter, all data members are used or required by the module. The data types could be of the int data type, float data type, char data type, etc. So the parameters of the two modules should be the basic data type rather than some maybe a different kind of a data type. These are the simple data types. So the strengths and the weaknesses: a module sees only the data elements it requires, and it is the loosest form of coupling because we are only passing the required data elements or the data types that the other module needs. Weakness: a module can be difficult to maintain if many data elements are passed. So we should not pass many data elements, rather only the required one, or very few of the data elements need to be passed. Next comes stamp coupling. Stamp coupling occurs between the modules when the data is passed by parameters using a data structure. Now, data structure could be a structure, it could be a union, it could be an array, it could be anything. So, previously in data coupling, where we have studied that the basic data types are to be passed, here we are passing a whole of the data structure at one go. For example, here we have a structure rectangle wherein these all are its values. This is an object of rectangle. Now when we are passing the whole of the structure, there what are we doing? We are passing the whole of the structure at once. As soon as this rectangle R would be passed, all these things will be directly passed towards this module, and these can be accessed. It is not necessary that all of them can be accessed, but yes, some of them can be accessed over here. So this is stamp coupling. Again, coming to the strengths and weaknesses, it is the loose form of coupling because we are only passing the data structure, and it simplifies the interface between the modules because one data structure can serve the purpose of many purposes. But the weakness that it has is it promotes the creation of artificial data structures. Why artificial data structures? If we look into the example over here, we have the rectangle R. This rectangle R has 1, 2, 3, 4, 5, 6, 7. 7 variables being passed over here, but we are just using the 2 of them. So rest 5 are unused in this module, but yes, they are passed. So they would be consuming some memory space. So that comes as a weakness over here because some artificial data structures are being used, are being taken up, but they are not in use. The next one that we have is the control coupling. In control coupling, as the name suggests, module A and B are said to be control coupled if they communicate by passing of control information. Now this control information is passed with the help of flags. So if we look into the example over here, we have module 1 and module 2 which are communicating with the help of flags over here. Now how is this flag working over here? We have this in a module A. Now if the flag value is true, then it would be solving some one of the thing. If the flag value is false, it would be executing some other thing. So this flag value is being passed from one module to another. If the flag is true, then some of the other things would be executed, and if the flag value is false, then another set of instructions would be executed. So instead of passing different values, here we are only passing the control. We just took a flag value. Initially, suppose the flag value is 0. We pass that flag value to the other. We need to check whether we have found a record or not. If suppose a record is not found, then what happens? It will just, if a record is not found, it will change the value of flag and again will return the value. So it is checking the flag value there, changing the flag value, again coming back to the first module, we'll check if the flag value remains the same, that means we got the data. If we did not, if the flag value changed, in that case it could be a possibility that the data was not correct, the data was not found, or the address that we sent or the ID that we sent was not correct. The next type of coupling that we have is a common coupling. Now, two modules are common coupled if they share the data through some global data items or the modules share common or global data or file. So, common coupling here talks about the sharing of the global data. That is, since the global data is being accessed, it can be changed by any of the module which is calling that data. This has the highest coupling in all of the hierarchy, because if you look over the example over here, we have this V1 and V2 as the two variables. Now, module X is changing V1 to 0, whereas module Y is incrementing V1, and module Z is adding V2 to V2 and A1 and storing the result in the V1 variable. Now, in this case, what is happening? Each of the module is changing the values of V1 and V2. Now, in case later at any part, we need to identify which module has calculated a different value or which where the bug actually exists, it would be very difficult to identify because all the modules are working on these two variables. And if a bug is found over here, it would be directly affecting this and it would be directly affecting this. That is why we should avoid using the common coupling because it is using the global variables. The next that we have is the content coupling. Content coupling exists between two modules if they share the code, example, a branch from one module into the another. For example, this is the example of the content coupling. We have a module A. Now, this module A is branched in module B and module C. That means this module B and module C would be using some of the data from module A. Similarly, if this module D and E are the parts of C, then some of the modules would be using the data from here. So, module B, if suppose we have here, it says go to temp. Now, this temp is being executed in module D. So, here this would be directly accessing the data from temp. So, this is how the whole of the content or a part of the code is being transferred from one module to another in case of content coupling. So, this is a hierarchy that we are taking about. Content coupling, because it is transferring the whole of the data from, it is transferring some of the code from one module to another. That is why it is considered the worst, because when the whole of the code is shared, then finding the bug and debugging is comparatively difficult. And then comes the common coupling and so on the hierarchy. The data coupling, where the parameters are passed in the form of simple data type, that is the loosest one. Now, how can we achieve this coupling? Controlling the number of parameters that are passed among the modules, we should only pass the required parameters in the module. It avoid passing undesired data. We should avoid passing undesired data to the calling module. Maintain parent-child relationship between the calling and the called module and pass the data, not the control information, as we have seen in the control coupling. Now comes the next topic, that is cohesion. Now, in coupling we have seen that the two modules are interacting with each other, they were interconnected with each other. Now, cohesion basically talks about the interconnection within the module. So, it is a measure of internal relatedness of the components of a module. Here we are not concerned about the different modules that are there, but yes, we are concerned about a single module and how the interconnections are being established inside a module. So, here we believe that higher the interaction between the elements in a module is there, better is the code. So, here we talk about high cohesion, while in the previous one we talked about low coupling. So, here we talk about higher cohesion and low coupling. So, these are the different types of cohesion that we will be talking about. The examples, the first one is coincidental cohesion where all the parts are not related to each other. Like we have separate functions which are not related to each other. The next one that we have is a similar logical cohesion wherein the functions are having similar type of logic in them and that is implemented in a module. Temporal, which is related by the time. All the variables should be interacting at a particular timestamp. Procedural, it depends upon the order of the functions, how function A is related to function B and then function B is related to function C. The next that we have is communicational, wherein all the functions in a module are accessing a single database. Sequential is in the top-down approach, starting from the first module, then the second, then the third, and so on. Functional, a function is divided into different parts, wherein it is sequential in nature with complete and related functions. So, starting with them in detail, the first one that we have is information cohesion. It describes a module performing a number of operations, each with a unique entry point and independent code, and all operations are performed on the same data. So, here we have a single input that is being done. That input is being executed by an independent code and all the operations are being performed on the same data that is being inputted from here. In information cohesion, each function in a module must perform exactly one action. Only one action needs to be performed. No other actions are performed in information cohesion. Coming to functional cohesion is said to exist if different elements of a module cooperate to achieve a single function. So, we have different elements in a module, they combine together, they cooperate together and only then one function is being achieved. Here, every element in a component is essential to the computation. It is not the case that if we have suppose 4 to 5 elements, only one element will be used in one of the execution and rest 2 elements will be used in another 2 executions. No, every element plays an important role whenever the computation of the elements or computation of the data is done. Sequential cohesion, module A outputs some data which forms the input to B. So, that is in a sequential form, starting from module A moving to module B, as we have just seen in the figure previously. So, here the output of one part is the input of another. So, whatever output we are getting from module A becomes an input to module B. So, in case a bug occurs over here in module A, then obviously it will be affecting the module B, because whatever output we have got in module A will serve as a purpose of input in module B. The next one that we have is communicational cohesion. A module is said to have a communicational cohesion if all the functions of a module refer to or update the same data structure. So, they communicate with each other. All the functions are communicating a same data structure over here and not the data. So, this data structure, what is it? A set of functions defined on any array or stack. So, array or stack is a kind of a data structure. So, whatever functions you are doing, for example, update the record in the database and send it to the printer, where what will it do? It will update the record on the database and then print the record. So, that is how the communication cohesion works upon. The next one that we have is a procedural cohesion. It is a form of a cohesion obtained when the software components are grouped in a module to perform a series of functions following a certain procedure. This procedure is not necessary that it is sequential in nature, but yes, a procedure is followed, a step-by-step approach is followed in order to execute a particular instruction. For example, here we have write output records. When an output record is being written, then a new input record would be read. It would be padded with spaces in case the input is not taken up with spaces. And then it would be returning the new record. Again, an output record will be, it becomes an output record which will be written onto a place and then the new records will be read. So, this is a procedure which is being followed. The next one that we have is a temporal cohesion. When a module contains the functions that are related by a fact that all the functions must be executed in a same timestamp. So this same timestamp is an important factor over here. What does it say? That all the functions must be executed. Whatever functions we are executing at a particular time, they should be executed at a particular timestamp, at a particular time. Only then this module is said to be exhibiting the temporal cohesion. So here the elements are related by the time involved. They are grouped by when they are processed, like they notify the user that yes, this maybe some update has been done, or lot of different activities occur all at the same time, maybe on a website or so. The next cohesion that we have is logical cohesion. It says a module is said to be logically cohesive if all the elements of a module perform similar operations. Now, that depends upon the logic. It basically works upon the logic. For example, handling the errors, data input, data output, etc. An example of logical cohesion is a case where a set of print functions are generated with different output reports. That could be, suppose if we are handling the errors, so whatever type of error is coming in, the user is typing an error, so that error is handled in different catch blocks. So when we are using the try catch block in a programming language, depending upon the type of the error, a logic is built. If one type of error would be there, this type of exception handling will be done. If this type of error comes, then this type of exception handling will be done. So this comes under the logical cohesion, wherein the elements of the component are related logically and not functionally. The next one is the coincident cohesion. Coincidental cohesion exists in modules that contain the instructions that have little or no relationship to one another. They are totally independent from each other. So the parts here, the parts of the components are unrelated. That could be unrelated functions, processes, or data. So unrelated, they are not affecting the working of one module or one the working of one process is not affecting the working of the other process. So again, the hierarchy that we have is, the best one that needs to be used is a functional cohesion, wherein the functions are being, if a module is having multiple functions, they should be interacting with each other, followed by sequential, communicational, and so on. Coincidental cohesion, wherein all the processes are independent of each other, that is the worst cohesion that ever exists. So now coming to the relationship between the cohesion and coupling, it says if a software is not properly modularized, a host of seemingly trivial enhancements or changes will result into death of the project. So as we discussed previously, that higher coupling and low cohesion is not recommended. It should always be that we should have the higher cohesion and low coupling. If that is not the case, then whatever maintenance we are doing or whatever error bug finding we are doing, any changes that are being made in a software, that can result into the crashing of the software. So we should always go with higher cohesion and lower coupling, and not with higher coupling or lower cohesion. Thank you.